Hi everyone, my name is Ariane Simeoni and I'm going to introduce you to our new paper entitled Unsupervised Object Localization, Observing the Background to Discover Objects. Our method, named Found, performs unsupervised object localization. We propose a simple framework in which we train a single Conv11 layer. We train our model for only 2 epochs over a dataset of 10,000 images, and inference runs at 80 frames per second. Results here are without any post-processing refinement. So how does it work? Our method is 2 steps. First, we propose to look for the background instead of objects and perform background discovery. Then we train a lightweight 1-1 convolutional layer to extract information from a self-supervised backbone. It is trained in a self-supervised fashion using the coarse background masks as pseudo-labels. We found we are able to produce good quality object localization on images from different domains, as you can see here. On the right, my friend is fighting his way through a hard boulder in Fontainebleau at Paris. So now let's get into details. Let's start with related works, and for a matter of time, I will only focus on methods leveraging self-supervised features. Let's start with Lost. That is one of our prior works, which uses patch similarities and finds the object seed, which is a patch with least connection to others in a similarity graph. All connected similar patches to the seed are considered as the object. On the other side, the concat and deep spectral method refine this result by using a normalized graph cut. Self-mask generates several potential masks by performing graph cut with different self-supervised features and then vote for the best one. And finally, FreeSolo compares patch features with different queries before filtering and ranking the produced masks. All of those works have shown that those masks can be used as pseudo-ground truths to train either detection or segmentation models. And it has been shown that after training, results are greatly improved over the initial mask. So how do we compare to those? Our approach Found enables us to create coarse masks by looking for the background instead of objects, and this without making hypotheses about quantity or shape of objects. Compared to others, we train a very lightweight model, a single Conv11 layer, which is trained in 2 hours on a single GPU. We show that there is no need for a large detector segmentation model. Also Found runs at 80 frames per second, which is much faster than compared methods. With such a small model, we're able to reach state-of-the-art results. Let's now talk about the background discovery step. So first, we feed the image divided in n patches into a self-supervised backbone model, in this case, a VIT model. Then we extract the self-attention maps in the last layer. And we find the background seed, which corresponds to the patch with the least attention in A, which are the attention maps. Once we have this seed, we can compare it with all other patches and select those that have a similarity above a certain threshold, corresponding then to our background mask that you can see here. This is a very simple method which discovers well the background, as you can see in those images, even though the maps are a little noisy, but objects are not selected, only background. So now we have the step of self-supervised refinement. In this step, we propose a segmentation head, which consists only of a single 1-1 convolution. For each patch, the convolution compresses the patch features into a scalar, which is then passed into a sigmoid function to encode the probability of the patch belonging to the foreground or not. We train this lightweight model by exploiting our background mask. We produce first a coarse foreground mask, which is simply the complement of the background mask. We then train the model to predict a smooth version of this foreground mask. And we additionally have an objective, which is to minimize the binary cross entropy between the output and its refined version after binarization. And we've actually observed that this helps with improving the edges of the produced mask. In both objectives, we use the bilateral solver to refine the pseudo labels using pixel information. So now some results. Here are the background masks. Here are the complement, which are the foreground masks. We have the foreground mask after refinement, so after bilateral solver. And finally, here are the results that are produced by Found, which you can see is well localizing objects and is quite smoothed on the edges. So now more details and results. So we are using as a backbone a bit smaller of patches 8, which has been trained in a self-supervised fashion using Dino. Found is trained for only 500 iteration on .tr, which is only 10,000 images for around 2 epochs. We evaluate on diverse images from the dataset like Pascal Vogue, Coco, .omron, and CSSD, and we show that we obtain great results in all of them. So in terms of results, we wanted to avoid having big tables on slides. So I invite you to check the numbers in the papers. But we produced results for unsupervised object discovery, the task. So in the task requires to discover at least a correct single object in the image. We also evaluate ourselves on the task of unsupervised saliency detection, which aim at to discover the salient objects. And finally, we evaluate on supervised semantic segmentation retrieval task, where features are computed per object mask before performing retrieval. In all cases, we achieve state-of-the-art results with a lighter and faster model. So as I've just said, we have a method which is lighter and faster. Found is fast at training and inference. Our model is just a single 1-1 convolution trained in 2 hours. And in terms of learnable parameters, we are less than 1,000 when other methods that require training use models that are above millions. Additionally, our model runs very quickly. So at inference, we are running at 80 frames per second, including the features extraction through the backbone and our layer. And this is much faster than all of the other methods, which include training or not. We show here that Found is able to generalize to out-of-domain images. Here you have images which have objects of different scales and are object-centric or not. And Found is able to localize objects well in all cases. So it's time for me to wrap this up. A last video to leave you, and thank you a lot for your attention. And come and talk to us during the poster session. Thank you.